Hello, my name is Matthias Gonda and I work at the University of Innsbruck in Austria. This is a pre-recorded presentation for the 2022 conference of the Society for Mathematical Psychology. The topic is about using Prolog from the R statistical programming language. This is joint work with Jan Wielemaker, who is the programmer of SWI Prolog, which is an open source implementation of Prolog. Prolog is a bit different from other programming languages, but not too different. Many of us are used to functional or imperative languages, like R on the left side for power calculation. In an imperative language, we basically tell the computer what to do first and then what to do afterwards. In a declarative language like Prolog, we define rules that kind of state what is true and under which conditions. For example, on the right side, we have the transitive closure of an arrow relation in which a node y is a descendant of another node x if x equals y, or if there is an arrow from x to z and y is a descendant of z. Yeah. I'll illustrate this here. So here we see the equality operation, so that x is a descendant of itself. Whereas here we have an arrow from x to z, and z is then a descendant of y. So let's look at sentence parsing, which is an example where Prolog really shines. On the right, we have a grammar with sentences, nouns, verbs, and participles, as well as a lexicon with a few words. Now we would like to parse the sentence, John sees a man with a telescope. And we get two possible parse trees, one in which John uses a telescope and sees a man. This is on the left side, and the other one in which John sees a man who carries a telescope. The motivation of rolog is to connect R and Prolog to solve a larger class of problems in statistics and artificial intelligence. Because the programming paradigms are so different, I anticipate that we gain a lot by combining them. So let's look at a few examples. Installation is very easy because the package is already available on CRAN, so you just type in or use it from the menu, install packages, rolog. The typical workflow is to load the package and then consult a Prolog program. Then we can create queries from R to Prolog. Because the two languages are quite different, you'll see that the syntax is a bit cumbersome. Therefore, one would typically wrap the queries into R functions with a simpler syntax. And then we submit the queries to Prolog and collect the solutions. Let me illustrate it using a family tree example, which is kind of a hello world in Prolog. On the top right, you see the Prolog program with the facts and rules. The facts state the parenthood between people. The rules define an ancestor relation. So x is ancestor of z if x is parent of z, or x is ancestor of z if x is parent of y, and y is ancestor of z. So this is a recursive definition. Now we can ask, who is the ancestor of Jim? In Prolog, we would simply query ancestor uppercase X Jim. In R, you see it's a bit more typing because we have to construct a call with a variable wrapped in an expression and the symbol Jim using quotes. But I mean, you'll get used to this. If we submit the query, we obtain Pat and Pam as the two ancestors of Jim. Now let's do something that is more useful. Suppose we can represent causal effects by the arrows of a so-called directed acyclic graph. And then we want to estimate the causal effect of an exposure E on an outcome D. And a typical question in the applied area would be, which variable do we actually need to adjust for? So on the right, you see an example based on classical work by Greenland et al. With an exposure, with a disease, and with some possible confounders like air pollution level, gender, and bronchial reactivity. Greenland et al. Present the so-called backdoor test for D-separation, stating that a set of variables S is sufficient for adjustment if 1. Every unblocked backdoor path is intercepted by a variable in S, and 2, if every induced unblocked backdoor path is also intercepted by a variable in S. Induced means that it is unblocked by our adjustment in step 1. And it turns out that these conditions can be represented by very concise Prolog code, which you can see partially on the right side. Here I query the problem from R and I obtain 2 minimal sets of confounders that need to be adjusted for A and C or B and C. So we need to control either for A and C or for B and C. Here I have a little e-learning application. My students often make mistakes when calculating things. For example, they forget the square root around the n in the t ratio, or they omit the parentheses around the numerator and the denominator of a fraction. Using Prolog, we can represent these 2 buggy rules in a very compact form, and we can use Prolog's nice pattern matching functions together with simple search algorithms to produce wrong response alternatives that can be matched against the student's responses. Note that Prolog is actually able to combine the buggy rules, so we need not to take care of this ourselves. So in the 4th example, you see the combination of the 2 buggy rules, the thing with the parentheses in the fraction, as well as the omitted square root. This example is for R users that want to generate reports from their analysis using the R Markdown language, or for people interested in programming Shiny apps. As you probably know, showing nice equations in R is a bit of a pain. It often looks like on the right side. The situation is a bit better in recent R versions, but if you want to have a nice mathematical typesetting, you basically need to do this yourself and type in LaTeX commands. The problem is now solved using rolog. You can translate the R expressions easily into MathML or LaTeX so that they look pretty in your report or on your website. On the right, you can see a quoted term in R, which is the binomial distribution. And with help of the Prolog bridge, you can either render it on screen in nice mathematical typesetting, and at the same time, you can calculate with it, as shown below, using the eval command. In other words, the same R objects are used for display and calculations, which is one more step towards reproducible science. The example on the right also illustrates that rolog can ring back to R to find out the name of the integration variable in this example. So we have a custom function g with variable u, and you see below that rolog has found out the name of the integration variable in the integral, which is not represented in this term. Actually, it needs to search for the name of the integration variable in the custom function u. So the communication is possible in both ways. This is the last example, which with a bit of a rusty syntax on the R end. Let D denote something between 5.7 and 5.8, and S be something between 3.8 and 3.9. Mu is 4 and N is 24. And these numbers may result from hand calculations or some intermediate results of other calculations. Now we want to calculate the t-ratio. In which interval will it be? And more generally, we ask for rules for interval arithmetic that propagate inputs within given bounds to intervals in the results. Some of these are even non-deterministic in a sense that division by an interval that crosses 0 yields actually two possible solutions, which is a perfect scenario for Prolog. So here we see the result of the t-ratio, something between 2.135 and 2.321. And we can now match this against the responses of our students in an e-learning system, for example. In fact, the e-learning system already exists, and that makes use of all the combined power of Prolog and R. On the right, you can see the feedback to a wrong response generated by math rendering functions in Prolog. If you want to contribute to this, you are more than welcome. This is a work in progress, and if you wish, contact me for developing useful R extensions that make use of the Prolog language. Thank you for watching this.